Hi and welcome to my series on solving the wave heat and Laplace equations. In this video we'll be solving a wave equation with a slightly more difficult initial condition to all the previous videos. As a prerequisite, you should be familiar with solving first and second order linear ODEs, and preferably we've been introduced to PDEs as well. So the first thing you're going to want to do, step 1, is to interpret what's going on. So I've already covered this in some previous videos, so I'll just really go through this really quickly. We can imagine we've got two people here and they're each holding the ends of a rope, and there'll be an impulse sent through the rope, and these people are just going to have their hands quite slack. So what they're going to do, so the Neumann boundary conditions just mean that the ends are allowed to freely vibrate. So that's all the Neumann boundary conditions mean in this case. So I'm going to move on because I think we've covered this several times in the other videos. So step 2, assume the solution to the PDE takes the form of u little x little t equals big X of little x big T of little t. Now if we sub this back in to the PDE, we're going to get something that looks like this. Now, step 3, we're going to want to use the method of separation of variables, and I'm just going to write SOV for short. So all we're doing here is putting all the t variables on one side and all the x variables on another side. If you've watched my previous videos, you'll know that I always put the constants and any other variables I have with the t, and I keep the x's all by themselves. And I say any other variables I might have because we're not always doing a wave equation. Maybe we're doing a modified wave equation. And because t is a variable that is completely independent of x and x is completely independent of t, and yet they equal each other, we can say that they must be equal to a constant, and we're going to call that constant k. Now, if you've watched my previous videos, you'll know that we can write k as negative lambda squared, and that is simply because k greater than 0 gives only the trivial solution, which tells us what happens when nothing happens, so we don't care about the trivial solution. And that is for Neumann conditions and Dirichlet conditions. So if we rearrange, we get two ordinary differential equations that we're going to solve. We get x double prime plus lambda squared x equals 0, and we get t double prime plus lambda squared c squared t equals 0. I'm going to put a box around these. Right, so step 4 is to use the boundary conditions, which should both be homogeneous. If they're not, you need to use another method to make them homogeneous, but that is a separate video. So use the boundary conditions with our ODE x double prime plus lambda squared x equals 0. So we use these for our boundary conditions, and we'll use these for our initial conditions. So in the case, you'll see that we've got two options for the sign of lambda. So we can have lambda is greater than 0, and we can have lambda equals 0. Now, if you've done a few of these before, you'll know that because this is a Neumann boundary condition, our lambda equals 0 case will not be trivial. So our eigenvalue will start at n equals 0, but I'm going to walk through the workings out of this anyway. So starting on the left-hand side, we get our ODE is x double prime plus lambda squared x equals 0. Now the general solution has the form. So this is just solving ordinary differential equations, so you should be familiar with this already. It's the form big X of little x equals a cosine lambda x plus b sine lambda x, and that is for where a and b are some constants. Now, because we've got Neumann boundary conditions, we just need to take the derivative of this before we can plug in our x values. So we get negative a lambda sine lambda x plus b lambda cosine lambda x. Now, plugging in our initial conditions, we had x equals 0. So if x equals 0, we're just left with b lambda, and that has to equal 0 as per our boundary conditions. So this just implies that b equals 0, because for this case, this is a case where lambda is greater than 0, so it can't be lambda. Now we plug in our second our second boundary condition, which is when x equals 1, and this also has to equal 0. So we get negative a lambda sine of lambda, the x just goes to 1, and that's supposed to equal 0. Now we can't let a equal 0 here, because if both a and b equal 0, we just get the trivial solution, which again we're not interested in. So what we need is for sine of lambda to equal 0, and we know when sine equals 0. So this just implies that lambda equals pi n, where n is an integer, and we can say n starts at 1, 2, so on. And that's simply because lambda equals pi n, so the n is in there as well, and we've said that lambda can't be negative, and it also doesn't equal 0, so our n does not start at 0 here. So this leaves us with an x of n. So this is, I should write this here, this is our eigenvalue, and that's the value lambda takes when we're not getting the trivial solution, when we're getting an interesting solution. So this, our eigenfunction here is just going to be cosine n pi x, and that is for n equals 1, 2, so on. This is our eigensolution. Eigenfunction. Now you can also write it with a constant in there. So, and that's because a multiple of an eigenfunction is also an eigenfunction. So you may see it written with a constant in there, or you can write it without the constant, either way. It's usually written without the constant, but both are correct. So now if we go to the right-hand side, if lambda equals 0, our ordinary differential equation takes the form of x double prime equals 0, and this has the general solution of the form big X of little x equals a little x plus b, where a and b are some constants. They're not the same constants as what I've written on the left-hand side. I'm just reusing a and b. Because it's a Neumann boundary condition, we need to take the derivative. So we'll get x of little x of x, and that will just equal a. Now if we put in our boundary conditions, we'll get x of little x of 0, so x equals 0 here. We still just get a because we don't have x in there, and that has to equal 0. If we put in the second boundary condition, x of 1, we still just get a, which equals 0. So we're actually left with an x naught of x equaling b, where b is just some constant. So now we can write the proper eigenfunction, which takes into account both lambda equals 0 and lambda greater than 0 cases. So I'll write it over here, write x of n of x, and that can equal 1 for n equals 0. So we have b up here, and I've just written 1 because, as I've said, a multiple of an eigenfunction is an eigenfunction. So b is just any constant, so I'm just going to write it as 1, and it can be multiplied by anything. So both are correct. You could also write just b here for some constant b as well. And I'm also going to write cosine n pi x for n equals 1, 2, so on. Now another way of writing this is x of n of x equals some constant a times cosine n pi x, and that should be a of n, for n equals 0, 1, 2. So that takes into account both of those cases here. So you can write it either way, both are correct. Okay, so step 5 is to use the homogeneous initial condition, provided you have a homogeneous initial condition, with the ODE t prime plus lambda squared c squared t equals 0. If you don't have a homogeneous initial condition, you just need to write the general form of the solution that the ODE up here takes, and then you'll multiply that with your x of n. So in this case, we also need to consider the lambda greater than 0 case and the lambda equals 0 case. So for lambda greater than 0, we get the exact same ordinary differential equation, plus lambda squared c squared t equals 0. This has the general solution of the form big T little t equals a cosine lambda, which is n pi, and then we've also got ct, plus b sine n pi ct. And then if we plug in our initial condition, now the homogeneous initial condition was a Dirichlet condition, so we don't need to take the derivative. We'll just plug in t equals 0, and that's going to give us a that has to equal 0. So now our t of n of t, if a equals 0 up here, then we just end up with a sine n pi ct. And again, you could write b sine n pi ct. That's also correct as well. So this is for n equals 1, 2, so on. Now for lambda equals 0, we get the ODE t double prime equals 0, which has a general solution of the form big T of little t equals A little t plus B, where A and T are some constants, again not the same constants as on the left hand side. If we plug in the homogeneous initial condition where T equals 0, we just get B, and B has to equal 0. So we can write T of naught instead of T of n, it's just where n equals 0, of T equals A naught of T. So again, I didn't necessarily have to write the A naught, I could have just written the T. Again, neither way is wrong, or it's probably more right maybe to not write the A of naught. But then if you don't do that, you have to make sure you do put the constants in when you're writing the general form of the solution, the x of n times t of n. We have step 6, so step 6, and that is to write our u of n x of t equals x of n x t of n t. And then if you've written these, the u of n and u naught separately, we can write u of naught x of t equals x naught of x plus t multiplied by t naught of t. So I'm going to write u of naught x of t equals a naught t, because we're just multiplying some constant up here, or 1, by this one here, a naught of t. So we just get a naught of t. Or if you use some constant back for x of n, x naught, you'll just get some constant times some constant a naught, which is again just some constant. So we're just going to continue calling it a naught, even though that a naught is could be a different a naught. So we also have a u of n x of t equals a n cosine n pi x sine n pi c t, and that is for n equals 1, 2, so on. So if you didn't write any of the constants in for x of n and t of n, just make sure you do write them in here. So I'm going to put a box around these because these are pretty important. And then we'll just make sure we write in for some constants a naught and a of n. So this solution takes into account all of our homogeneous conditions so far. Now the next step is step 7, and that is to plug in the non-homogeneous initial condition. So that'll be into either u naught or u of n, whichever one feels more appropriate. In our case, our non-homogeneous initial condition looks like this. X naught equals x1 minus x. So you'll see that our u of n case will be more appropriate here. So normally I'm going to go through what we've done in all the other examples and then show you why that doesn't work here and show you what to do instead. So normally what you would do is, because we've got a derivative here, we need to take the derivative of u of n. So we'll say u of n of t for x of t, and that will equal a n n pi c cosine n pi x cosine n pi c t. Now then we would plug in t equals 0, so we're matching that non-homogeneous initial condition. So u of n of t x 0. So t equals 0, and that goes to a of n pi c cosine n pi x equals x 1 minus x. Now you see that if we go and solve for a of n here, normally the next step would be to solve for a of n and n. You'll see that there's no way that a of n here can be a constant, and a of n is a constant. We've defined it that way. So if we solve for a of n, it's not a constant. What do we do? What we're going to need to do instead is to use the superposition principle. So what we can do is we can write, so I'm going to say, put a big X next to this and a little line underneath here. So what we can do is we can write u of x of t as a naught of t over 2 plus the sum of n equals 1 to infinity of a of n cosine n pi x sine n pi c t. So here I can say use superposition principle to rewrite u of x of t. So we write it in this other form here. So our a naught of t, that just comes from our u of naught. So that's our n equals 0 case, and that goes out the front. So it's whatever u naught is over 2. And then we have plus, and then we just have the sum of our u of n here. Now if we write it like that, then what we're able to do is we can use the Euler formulae to solve for a of naught and a of n here. So what we first need to do though is we first need to take the derivative. So our u of t x of t is now, if we take the derivative of this, now we just get a naught over 2. Remember, a naught is some constant, and so is a of n, plus sum n equals 1 to infinity of a of n n pi c cosine n pi x cosine n pi c t. So now if we plug in our t equals 0 case, we just get a naught over 2 plus the sum of n equals 1 to infinity of a of n n pi c cosine n pi x. So what I'm going to just do really quickly is rewrite this ever so slightly differently, just to help in my workings out. I'm going to call these constants at the front here, I'm going to call them a of n bar. So cosine n pi x. And I'll just remind myself that a of n bar equals a of n n pi c. So we can use, so step 8 is to actually use the Euler formulae. to find A naught and A of n. So you'll notice that there's also a B of n as well for the Euler formulae. We don't need to use it in this question, but that also exists. So for A of naught, the Euler formulae looks like this: 2 over L from 0 to L, f of x dx. So L in this case, for the wave heat and for the wave and heat equations, we say x goes usually from 0 to L. In this case, our L is 1, because if we go all the way back up here, we go from 0 to 1. So our L is just 1 in this case. So we can just rewrite this as 2 over 1, so it's just 2 from 0 to 1. And our f of x is just the non-homogeneous condition value. So it's just x, 1 minus x dx. So all we need to do is compute that integral and we'll get our value for A of naught. So I'll just do this in another color. If I compute this, we get 2x squared over 2 minus x3 over 3 from 0 to 1. And that just equals, doing that quickly, 1/3. Okay, so now we'll just do our next one. So our next one is A of n. Oh, sorry, it's A of n bar, not A of n. Very important. So there's a few other constants. So we'll go through and compute this integral and then we'll resolve for A of n. So it's 2 over L, 0 to L. Now this time we have f of x times cosine n pi x over L dx. So recall that our L is 1. So we'll just have 2, 0 to 1, x of 1 minus x cosine n pi x dx. And now to do this, we're going to need to use integration by parts, or in my case, I'm going to use the DI method, but that's basically integration by parts. That's where it's come from. So I'm just going to really quickly compute this. So if you are interested, I've just taken the integral. So the I just means the integral and D is just the derivative. And then all I'm going to do is multiply these, and these here. I'm going to change to green here. Right, so what we get, don't forget, I might do it down here where there's a bit more room. What we get is that 2 out the front. And then if I multiply these things, 1 minus x, I've just rewritten this as the x times 1 minus x because it looks a bit neater. Multiply it by this down here, n pi sine n pi x. Now we're going to get a that will be negative there. Don't forget the negatives. So actually, yeah, it's going to plus, and we're going to get 1 minus 2x over n squared pi squared cosine n pi x, and we're going to get another negative plus negative, so we're going to get plus 2 over n cubed pi cubed sine n pi x and that is going to be from 0 to 1. So what I've done is multiplied these, and then I've added those three terms together. So that gives us, that is equal to this here. All right, so now I just need to simplify and hope I don't make any mistakes. I'll be honest, this isn't my favorite part. So if we put in 1, we're going to get 1 minus 1, and that's just going to go to 0, so that whole term will go to 0. 1 minus 2 is going to be a minus, whoops, don't rub it out, 0 minus 1 over n squared pi squared cosine n pi plus 2 over n cubed pi cubed sine n pi, and that's the first term here. Going to minus the next part, 0, sine will vanish, plus 1 over n squared pi squared plus 0. Let me know how many mistakes I make down below. So this, cleaning it up further, minus 1 over n squared pi squared. Now the cosine n pi, we can just rewrite this as minus 1 to the n, because it will just alternate depending on what n is, to 1 to minus 1 to 1 to minus 1, and so on. You'll see that those things are the same. A bit further, we get minus 1 over n squared pi squared. Yep, because the sine of n pi also vanishes, because that will always equal 0. So then we get, simplifying further again, minus 1 over n squared pi squared to minus 1 to the n plus 1. And then, so you'll notice now that we get a few different values here, because if n is odd, we're just going to get 0. But if n is even, we're not going to get 0. So this just goes to, say, minus 1 over n squared pi squared, and we multiply it by 2 for even n, and multiply it by 0 for odd n. So what we get here, this is a of n bar equal, and if we recall, it equals a of n n pi c. So if we then solve for this, implies that a of n now equals minus 2 over n squared pi squared, and that is all over n pi c. So a of n is going to equal minus 2 n cubed pi cubed c, and that is for even n. I might just rewrite this again so it's a little neater. A of n equals minus 2 over n cubed pi cubed c, and that's for even n. Now because it's even, I'm actually just going to write, replace n with 2n. So replace n with 2n. So everywhere we see an n, we're going to replace it with a 2n. So I'll rewrite our final solution now that we've got both a of n and a naught. Remember, a naught was 1/3. So if we rewrite, so we'll go back to this here. So actually I might just copy that instead of rewriting it. So if we fill this in with our a of naught, remember our a of naught was a third, so we just end up with t over 6 plus n equals 1 to infinity. Now you can just write like n odd. It depends on how your teacher likes you to write it. My teacher doesn't like me to write it that way. So I replace, for every n, we're just going to write 2n. So we're going to get something that looks like, I'll write it the first way first. N cubed pi cubed c times cosine n pi x times sine n pi c t. So that's the case where you would say for n even only. But we can also write it this way. So we'll say t over 6 plus sum of n equals 1 to infinity. We're going to get minus 2, and we're going to just plug a 2 in with the 3. So we'll say the 2 in with the n. So 2n pi, and that is all of those terms are cubed, times c cosine 2n pi x times sine, and that is 2n pi ct. So that is our u of x of t. And now this thing here is our specific solution, and it fulfills all of our conditions. So this is our specific solution. Hopefully this wasn't too tedious for you if you don't enjoy maths. I don't think anyone enjoys doing all the simplifying up here. I certainly don't. Give me a thumbs up if you thought this was helpful. If you thought it was really helpful, subscribe to my channel. I aim to upload videos at least every week, if not more. Thanks, and hopefully see you all in another video.